Hello, class. Today, we are diving into two fundamental concepts of computer architecture: the machine cycle and computer bus. Think of the machine cycle as the internal heartbeat of the CPU. It's the repetitive process the computer uses to fetch, decode, and execute every single instruction we give it. But the CPU doesn't work in isolation. To get its work done, it needs a way to move data to and from memory and other parts of the system. That's where computer buses come in. These are the high-speed data highways or electronic pathways that connect everything together. By the end of this session, you understand not just how a computer processes data, but how that data physically travels through the machine. Now the strand: computer architecture and organization. Substrand: data storage and manipulation. Learning indicator: understand and explain the control bus, address bus, data bus, and the internal clock. Machine cycle: fetch, decode, execute, store cycle, instruction set for a CPU, and describe embedded systems. Focal area for today: describe the steps involved in the machine cycle, fetch, decode, execute, store, that's FDES cycle. Explain the role of the address, control, and data bus in the machine cycle. Learning objectives: by the end of this lesson, you'll be able to identify and describe the three types of computer buses: control, address, data. Explain the role each bus plays in connecting the CPU to memory. List the 4 stages of the machine cycle, FDES. Describe what happens at each stage of the machine cycle. Explain how buses are involved in the fetch stage. Trace a simple instruction through the complete machine cycle. The last time, we explored the big 3 components of the central processing unit. First, we have the control unit, CU, which acts as the brain's manager, directing the flow of instructions. Second, the arithmetic logic unit, ALU, where all the heavy lifting, that's the calculations and the logical true or false decisions, takes place. And finally, the registers such as the MAR, PC, and MDR, which serve as the CPU's ultra-fast temporary storage spots. But here is today's big question. We know what these parts are, but how do they actually work together to execute an instruction? That is exactly what we are going to solve today. Note: please make sure your notebooks are open. we have several activities and reflection questions coming up, and you want to have these key components written down as a reference. So what exactly are computer buses? In the simplest terms, a bus is a communication channel, a physical set of parallel wires or optical paths that connects the CPU to every other component in the system. I want you to visualize these as highways. Just as a highway transports cars and trucks between cities, these electronic highways transport information between the CPU, the memory, and your input-output devices. The key point to write down here is this: without buses, the CPU would be isolated. Buses are what allow instructions and data to move fluently around the entire computer system. They are the infrastructure that makes communication possible. As you can see in figure 1, the communication between the processor and the main memory isn't just one single wire. It is divided into 3 specialized channels. First, we have the address bus, which carries information about where data needs to go. Second, the data bus, which carries the actual information or instruction being processed. And third, the control bus, which carries the commands, telling the system whether to read or write data. A very important term for your notes is the system bus. When we group these 3, address, data, and control, together, we refer to them collectively as the system bus. They work in perfect synchronization to ensure that the right data gets to the right place at the right time. Let's break down the key distinctions using simple questions, which you can see summarized in the table on your screen. The address bus answers the question, "Where should I look?" It points to a specific location in memory, like a house number on a street. It only sends an address out from the CPU. The data bus answers the question, "Here is the information." This is the main carrier. It transports the actual content, the data or the instruction itself. The control bus answers the question, "Do this now." It provides the commands like read from this address or write this address, ensuring timing and coordination. Now for the important technical details regarding the directionality. The address bus is unidirectional, one way, from CPU to memory only. Because the CPU is always the component that initiates a memory access. Conversely, the data bus and the control bus are both bidirectional or two-way. Data needs to flow to memory when writing and from memory when reading. Control signals are needed by both the CPU and the components to coordinate this flow. The CPU follows a precise, repetitive process to execute every single instruction we give it. This process is called the machine cycle, also known as FDES cycle. Fetch, decode, execute, and store. Think of it like a continuous loop. Fetch. This is where the CPU goes to memory to retrieve the next instruction. Decode. The CPU interprets what that instruction means. It figures out what to do. Execute. The CPU performs the actual action, usually involving the ALU we discussed earlier. Store. The result of that action is saved back into memory or a register. Two key concepts are vital here. First, the CPU repeats this cycle continuously to run all programs, processing one instruction at a time. Second, every step is perfectly synchronized by the CPU clock, which generates regular electronic pulses, ensuring all these operations happen at just the right microsecond. In the first stage, the CPU's primary job is to retrieve or fetch the next instruction from the main memory or RAM. This stage is a beautiful example of how the CPU components and the buses work in perfect harmony. There are 6 precise steps involved. Step 1. The program counter register, that's PC, is crucial here. It always holds the memory address of the next instruction we need. Step 2. That address is sent out along the address bus, pointing to the exact location in RAM where the instruction is stored. Step 3. The control bus then sends the specific read signals to the memory system, authorizing the transfer of data. Step 4. The actual instruction then travels back from RAM to the CPU via the data bus. Step 5. This incoming instruction is temporarily stored in a vital register called the Memory Data Register, MDR, within the CPU. Step 6. Finally, the program counter is increased by 1 to prepare for the next fetch cycle. Remember, as you can see, all 3 buses are essential just for this first stage. The address bus points, the control bus commands read, and the data bus carries the instruction back to the CPU. Imagine you've just received a letter in a language you don't speak. You have the paper in your hand. That is the first stage. But until you translate it you can't act on it. This is exactly where the decode stage comes in. It is the aha moment for the CPU. The heavy lifting here is done by the control unit, CU. Once an instruction is fetched, the CU breaks it down to identify two critical things. The opcode. This tells the CPU what to do. Is it an addition, a subtraction, or moving data from one place to another? The operands. This tells the CPU where the data is. It identifies the specific numbers or memory addresses needed for the tasks. The control unit then translates these findings into electrical signals that prime the rest of the CPU for action. Think of our recipe analogy. Add 2 cups of flour. Decoding is the part where you read that line and realize you need to grab the flour, that's data, and a measuring cup, that's 2, before you actually start mixing, that's executing. The most important thing to remember here, no work is actually being done yet. I repeat, no work is actually being done yet. At this stage, we are just setting the stage. Now that the CPU understands exactly what is required, it's finally time to do the work. Let's move to the execute stage. We have fetched the instruction, we have decoded the instruction, and now we arrive at the most dynamic stage of the cycle, the execute stage. This is where the CPU flexes its muscle and actually performs the task it was assigned. The execute stage is where the work happens. Different types of operations involve different components of the CPU. As you can see in the table in the slide, arithmetic and logical operations like adding two numbers or comparing values are handled by the ALU or arithmetic logic unit. Data movement operations are managed by the registers or buses system. Control flow changes like deciding to jump to a different instruction are managed by the control unit. Let's look at our add 5 plus 3 example. In this execution stage, the ALU received the numbers 5 and 3. The ALU performs the addition operation itself. The result 8 is produced and held temporarily in a register. The transition. The result is calculated, but it is not yet securely saved for long-term use. This final result is currently volatile and needs to be placed into memory. We have one last crucial stage to complete the full machine cycle, the store stage. We have reached the end of the line for a single instruction. The computation has been made, but if we don't save the result, the work is wasted. The store stage is about data persistence, making sure the computer remembers what it just calculated. In the store stage, the result of the execution, our number 8 from the addition example, is written back into memory or a specific register. This is a critical step because it ensures that the results are preserved. The program has the data available for the very next calculation it needs to perform. Where does it store the data? It depends on the instruction. Option 1. In a CPU register. If the data is needed immediately for the next instruction, perhaps we are adding another number to 8. It stays in a high-speed CPU register. This is the fastest access point. Option 2. Back in RAM. If the data isn't needed right away, it gets sent to a specific address in the computer's main memory, RAM. Slower than registers, but offers more capacity. Once this data is stored, the cycle is complete. The program counter advances, and the entire fetch, decode, execute, store cycle starts all over again for the next instruction. That completes our deep dive into the 4 stages of the machine cycle. We now know how one single instruction flows through the CPU, but all this information needs to move around on dedicated pathways. In our next section, we will switch gear and look at the specifics of those essential digital highways, the computer buses. This image shows a complete machine cycle showing all components. So you can see from the fetch from the RAM to decode the control unit to execute on the arithmetic logic unit, then store on the RAM. So a complete machine cycle. We have covered each piece of the puzzle individually. Now let's zoom out and look at how these components integrate to form a single, seamless, and lightning-fast operation. The crucial takeaway is that the entire cycle repeats continuously for as long as the computer is powered on. It processes one instruction at a time, but it does so incredibly quickly, synchronized by the CPU clock. These clocks operate at speeds measured in gigahertz, GHz, meaning billions of cycles happen every single second. Every part of the CPU works in concert. The program counter keeps the computer from getting lost, always pointing to the next instruction needed. The control unit is the conductor of this orchestra, managing the flow and decoding the instructions. The ALU is where the mathematical and logical work happens. Various registers like the MAR and MDR act as temporary high-speed storage locations for data moving in and out of the CPU. And underlining all of this communication are the buses, the address, data, and control lines, which facilitate all communication between the CPU and main memory, ensuring the right information gets to the right place at the right time. This integrated view highlights just how precise the timing needs to be. How the buses support the cycle. We have covered the stages of the cycle and we've defined the buses. The slide, in conjunction with the helpful table you see here, is the final piece of the puzzle. It shows how all these moving parts synchronize perfectly to process a single instruction. The machine cycle is how the CPU transforms instructions into action, using the clock as a conductor, keeping everything in synchrony. As the table illustrates, specific buses are active at specific times. During the fetch stage, all the three buses, address, data, and control, are busy retrieving the instructions from memory. For decode and execute, the communication is largely internal to the CPU, using internal buses to move the instruction to the control unit and data to the ALU. Finally, the store stage utilizes the data, address, and control buses again to save the final result back to the RAM if needed. The big picture takeaway is simple. The machine cycle provides the sequence, the buses provide the pathways, and the clock ensures perfect timing. Again, the machine cycle provides the sequence. The buses provide the pathways, and the clock ensures perfect timing. We have covered the theory. Now let's make it real. How does this theoretical fetch, decode, execute, store cycle apply to something as simple as clicking an icon on a desktop? The answer is every single step you take on a computer relies on this exact process. Let's walk through the act of opening a web browser as our primary example. The sequence you see on the slide happens in millions of cycles per second. Fetch. When you double click that icon, the CPU first retrieves the instruction. Open browser program from the system memory. Open browser program from the system memory. Decode. The control unit interprets this instruction to understand that it needs to locate the browser software files and load them into RAM. Execute. The CPU executes the complex task of actually loading all those program files from the storage drive into the active RAM. Store. Data regarding the browser's interface and initial web page is stored in memory so that it can be displayed on your screen. So every subsequent action, loading an image, typing a web address, clicking a link, involves thousands of these FDES cycles working in concept. It is truly the heartbeat of modern computing. We have a sequence of events: fetch, decode, execute, store. But how does the computer ensure that the decode stage doesn't start before the fetch stage is completely finished? The answer lies in the CPU clock. The CPU clock, sometimes called the internal clock, acts like a digital metronome. It generates highly regular electronic pulses. The speed of these pulses is measured in gigahertz, which means billions of pulses every second. These pulses ensure the entire operation is synchronized. Think of it this way: the clock pulse is the go signal. Only when the go signal arrives can the next stage begin. This control determines synchronization. It guarantees that every stage completes in the correct order and within the allotted time frame. Speed: a faster clock speed, higher gigahertz, means the CPU can complete more cycles per second, resulting in a faster computer. Timing: it controls exactly when the buses are active, ensuring data is sent and received at the precise moment required. This precise timing is essential for coordinating the flow of information. So what do these gigahertz numbers you see on a computer box actually mean in practical terms? They aren't just marketing jargon. They translate directly to how much work a processor can do every single second. The slide gives us a comparative look at different types of devices. The key takeaway is simple: 1 gigahertz equals 1 billion cycles per second. As you can see with our basic laptop, a 2.5 gigahertz processor runs 2.5 billion machine cycles every second. A smartphone running at 2.0 gigahertz is slightly slower at 2.0 billion cycles per second. The gaming PC really shows the difference. Its 4.0 gigahertz clock speed allows for a massive 4.0 billion cycles every single second, enabling much more complex and faster operations necessary for high performance gaming. Each of these cycles represents one full fetch, decode, execute, store sequence. So when you see that 4.0 gigahertz number, you know that CPU is completing the fundamental machine cycle 4 billion times every second. The clock is what controls the timing of the operations, and the buses what controls the movement of data. All right. We have covered the machine cycle, the CPU clock, and the fundamentals of the system bus. Now it's time for you to check your own understanding. These 6 questions are designed to test how well you've grasped the core concepts we've discussed. Please take out your notebooks. The most important part of this exercise is to be honest with yourself. Try to answer these questions without looking back at your notes or the previous slides first. Question 1 and 2 are simple recall questions. Question 3, 4, 5, and 6 require you to explain the interactions we've discussed, describing which bus does what and when, and the specific role of the clock. Take about 5 to 7 minutes to work through these on your own. This is the best way to identify areas where you might need a little extra clarification. That concludes our deep dive into the machine cycle and computer buses. You've all done some great work today absorbing complex material. We've laid a strong foundation, and now it is time to look ahead at where we go from here in our next lesson. In the coming sessions, we will shift our focus to 2 new exciting areas. Focal area 3, CPU instruction sets. We will explore the actual language the CPU speaks. What instructions does it actually understand? Focal area 4, embedded systems. We will look at where these systems are used in the everyday devices that make our world smart, like our microwave, car, and smartphone. Now that you know how the CPU executes instructions with the FDES cycle, think about what those instructions actually look like. Can the CPU understand the Python code we write directly? We will explore this fascinating question and much more in lesson period 2. For the preparation, think about devices around you that contain embedded systems. What makes them smart? Great work today, everyone. Look forward to seeing you in the next lesson.